Hello everyone, welcome to eSpace. I am Chandran. I am tech graduate from IC Bangalore, now working as senior engineer at Caltron, Trivandrum. Welcome to a new lecture, BJT as a switch. This lecture will be dealing about revision of BJT, analysis of BJT as a switch, design of BJT LED driver, design of BJT relay driver, and other variants of BJT as a switch like PNP, etc. About the lecture, this is mainly a theoretical course and some practical experiments we will be doing in TINA, a circuit simulator, and this is a BTech level course. References are Microelectronic circuits by Sedra Smith, integrated electronics by Millman Halkias, electronic devices and circuit theory by Robert Boylestad and Nashelsky. As a prerequisite, you should have a knowledge on basic mathematics, some algebra solving like that, network theory, mainly KCL, KVL, and Thevenin theorem, superposition theorem like that. And you should have a basic knowledge on BJT, a solid state device point of view of BJT. So before entering into a subject, we will do some revision on BJT. BJT is bipolar junction transistor. There is a flow of current by electrons and holes. That's why it is called bipolar. And there are two junctions. That's why it's called junction transistor. It's a three-terminal device with two semiconductor junction. Two variants are there, NP and PNP. In both differ by the direction of currents. These are shown here. This NPN, two junction, this base of NPN, this is a base, this is a emitter, this is a collector, and for PNP this is a collector, this emitter is a base, and the directions will be opposite because here it is full of electrons, this is full of holes, and the direction of current change is opposite to each other for these two variants. It's a two-port device. Suppose if you see here NPN, this is a input loop and this is an output loop. Both are isolated to each other. Both makes it a two-port device, and it's a current device because the IC here, the collector current is controlled by the base current here. It is beta times IB. If you are giving a 20 microampere current here, then you will get a collector current 100 times of it, that is 2 milliampere. And there are three regions of operations, that is cutoff, active and saturation. In cutoff, both the junctions are reverse biased. In active, base emitter junction is forward biased and collector base junction is reverse biased. And saturation, both base emitter and collector base junctions are forward biased. And it works as an amplifier, both voltage and power. Some special transistors are there which deal with power amplification. Power amplification, mainly the current will be more. There will be a power gain. For voltage amplifier, there will be a voltage gain, and works as amplifier. And a switch will be dealing with amplifier. It is working as a switch. And the IE, the emitter current here is sum of base current and collector current, that is IE is equal to IB plus IC, and current gain beta, that is IC equal to beta times IB. So let us understand BJT as a switch. Let us do an analysis for it. Here taken the transistor taken here, it is NPN transistor. So this is a symbol of NPN transistor, and this is a circuit as a switch. That's a base resistor connecting base voltage, and there's a collector resistor connecting the collector voltage. And here base emitter junction is forward biased, and it is when the switch is on. And here the collector base junction is reverse biased with this circuit. So there is a base resistor here, that is 82K. There is a collector resistor 1K here, and the supply is 5 volt. So for example, we are taking a TTL circuit, it will be 5 volt. That's why I have taken here 5 volt. And there's a base emitter loop and collector emitter loop. These two loops are isolated to each other. These two are different, two isolated loops. And in this base emitter loop, we'll do the KVL equation, and the collector emitter loop we'll do the KVL equation. Then these two equations, these are two different equations to find out IB and IC. And the first case when IB is equal to 0, where the switch is open now, so IB is 0, the base current is 0. So when the base current is 0, we will get the collector current is also 0, because it is, at the CE loop it is there is a current control current source, that is the collector current. So the collector current is 0 when IB is equal to 0. This is the open circuit. So here this side VCE, the collector emitter, in the collector emitter junction there will be a we can model it as a switch, and this will be open when IB is equal to 0. So now the switch is open in the collector emitter loop. Now, so the BJT now act as a off switch. When the switch BJT act as a off condition, and see, this condition is called cutoff mode. That is when IB is equal to 0, and for that IC is equal to 0. So let us now see the DC equivalent of BJT. So as I told, this is a base emitter junction, this is a collector emitter junction, and these two are isolated to each other, and these two makes a two-port network. And VB is the forward voltage of base emitter junction, and at saturation it is 0.7 volt. And the later condition we have seen that BB is equal to 0. So here it will be the voltage will be 0. So IB is equal to 0. So here the collector current beta IB, it will be also 0. This current source will be, this dependent current source will be 0. And beta is a DC forward current gain. So here it is shown, this is a current gain, this is a dependent current source which depend upon this current IB. So when IB is equal to 0, it will be 0, and in the other conditions, when IB is some value, there will be some collector current also flowing through this collector emitter junction. So let us now do the analysis through KVL equation. There are two meshes or loop to write the KVL equation. So one is, as I told, that is base emitter loop, and other is collector emitter loop. It's just like two ports of a two-port network. And base emitter loop is given as VBB is equal to IB RB plus VBE. So when the switch is open, IB is equal to VB is 0, that bias is 0, and the voltage at the base terminal it is 0. So IB is equal to 0. So according to DC equivalent circuit, here IC is equal to beta IB. That's at the collector current, the dependent current source will be beta IB, that is beta into 0 equal to 0. So collector emitter loop will be given as, is that equation we can write. This is the collector emitter loop KVL equation, that is VCC equal to ICRC plus VCE. So VC equal to VCC. So at the output of collector, at the collector terminal, the voltage will be VCC. So like we can just model it as a switch. At the collector emitter, the BJT act as an open switch, and this mode of operation is called cutoff mode. That is, a collector emitter loop is open, or the C collector emitter act as an open switch. That is we can model the BJT as a open switch. So at the collector emitter junction, that the switch will be open, and that behaves as an open circuit. So VC equal to VCC. So the switch we have seen, the circuit we have seen is a common emitter one. So there is a common emitter output characteristics. This is current at the y-axis, IC collector current at the y-axis, and collector emitter voltage at the x-axis. And this is the current for different values of input current, that is input base current. So now in this condition we have taken IB is equal to 0, so IC is equal to 0. So we'll see this common emitter loop, and now we'll introduce a new term called load line. So a load line is formed when there is a resistor in a active device circuit, or in a circuit like in a diode circuit, in a circuit including diode. If there is a resistor, there will be a load line for that. So here now the common emitter loop is given as VCC is equal to ICRC plus VCE. So here there is a resistor term here. So because of this resistor, there will be a load line at the output characteristics. And so now this can be written as intercepts of line with x-axis and y-axis. Here x-axis is VCE and y-axis is IC. So it can be written like this: VCE by VCC plus IC by VCC by RC. So now this term, this is a this, and this term is a x-intercept and a y-intercept. Y-intercept means here is a VC, IC is the y here, y-axis here. VC is the x-axis here. So this is a x-intercept and y-intercept here. So the above is equation is the equation of a line with intercepts at y VCC in VC axis and IC axis, and with slope minus 1 by RC, which is called the load line. So, and the intersection of this load line and output characteristics form the current and voltages at the output circuit. So it is here, it is written here. The output characteristics show the relationship between IC and VC. So the intersection of points of the load line and output characteristics is the possible values of voltage and currents of in IC and VC. So this is the diagram. So this is the CE output characteristics, and this red line is the load line. So the intersection of these points here will form all the voltages and currents available in the circuit when the IB, that is the input current, changes. Input current changes through these lines. It will take these values, that is IC and VC at these values. So here for amplifier it can be a Q point active region. At cutoff, this will be the point. When IB is equal to 0, this will be the IC value, and when IC is maximum, this will be the VC value, that is VC sat, and this will be the IC value, that is IC sat. So let us do the circuit analysis for IB is equal when IB is very at maximum current, that is at saturation mode. Now the base emitter junction is forward biased, and here VC is also forward biased, so it makes a mode as a saturation mode. So when IB is equal to max, IC is equal to max. So when the switch is closed here, these two junctions are forward biased, and we can find out that IB is this value 52.4. We'll consider in the next slide. So at the we'll take the equations in these two loops, that is base emitter loop and collector emitter loop. So we will write the base emitter loop as the base emitter loop KVL equation as like this: VBB is equal to IBRB plus VBE. So when the switch is closed, the bias voltage will be maximum, that we will get VB is equal to 0.7, that's at the saturation. You will get VB is equal to 0.7. So we will write IB as VBB minus VBE by RB, that is 5 minus 0.7 by 82K, that is 52.44 microampere. So again, according to DC equivalent circuit, we will get the dependent current source, that is IC, that is equal to beta IB. We will get beta into 52.44 microampere, that's equal to 5.24 milliampere. So when we substitute this value in collector emitter loop KVL equation, we will get VC at negative voltage. According to that, it is understood that the transistor is gone into saturation. So we will write VC equal to VC sat, that is the saturation voltage, that's equal to 0.2 volt, and substitute in IC equation, that is IC equal to VCC minus VC by RC. So we will write as 5 minus 0.2 by 1K, that is equal to 4.8 milliampere. So first we taken IB equal to some value. IB is equal to 52.44 microampere. At that value, this will be IC will be this value. At this value it will be. So but we'll take this VC sat as a VC voltage, and again find for IC is equal to VCC minus VCE by RC. We'll get this value, that is 4.8 milliampere. So consider this circuit. We are doing an experiment here. This is a circuit simulator in TINA. TINA is a circuit simulator. So this is a voltmeter here, and this is a voltage generator, that is a pulse generator which varies from 0 to 5 voltage, and it's connected to the same circuit, that is RB 82K and RC 1K, and here we are another connected to a voltmeter here, that is VM2 and VM1, and while simulating we will get these waveforms, VM1 and VM2 waveforms, at the oscilloscope in the simulator. So we see the waveforms here. This is the input voltage at the base voltage. This is the VM1. This is VM2. This is a voltage at the collector. This is a voltage at the base. So what is the inference is these are inverted to each other. So this transistor circuit act as an inverter where we can get the inverted waveform at the collector terminal given to a voltage source at the base terminal. So if you see the waveforms of discussed BJT circuit, the output waveforms is inverted to each other. So inference is that this circuit can be used as a BJT. So this circuit what's shown here can be used as an inverter with input voltage at the base terminal and taking the voltage at the collector terminal. Thus that both voltages will be inverted to each other. So it can be used in TTL inverter. It is already used as an inverter in TTL logic family. Another use is that it can be used as a relay or LED or relay driver. That is at the collector terminal, at the collector emitter, at that loop, you can connect a LED and then give a voltage at the base terminal, and with a small current we can drive a LED which takes more current, some 10 or 50 times greater current than at the base voltage base terminal. So for example, at the output voltage, that is the output port of a microcontroller, that will be a microcontroller cannot source that much current. Usually it will be maximum some 100 microampere. So if we give a 100 microampere at the base circuit, base terminal, it can drive a some 10 milliampere, taking 10 milliampere current at the collector terminal. And also different variants of circuit will be used that can be used in different applications. That will also, we will also discussing that. So this is the design of BJT as a LED. As I already told you, LED can be connected here, and here this can be a port of a microcontroller which gives a 5 volt, but it cannot source that much current as here. Here LED, suppose LED almost takes it takes a 5 milliampere current. Here it will be some 10 microampere, 100 microampere maximum, and when we give here, this transistor drives this LED and takes, here it will be this, here at the collector terminal it will be some 10 milliampere, here it will be some 10 microampere, 100 microampere. So there is a gain here. So this circuit acts as a driver for LED. So now we'll look at the design of that. So consider the below circuit. So we have to find out RC and RB. So first we'll consider in the collector emitter loop. So to glow a LED, there's a need of a current limiting resistor. Suppose we give a 5 volt to LED, we cannot predict how much current it will take. It can take maximum up to 100 milliamperes, and finally it may damage the diode, damage the LED. So we need a current limiting resistor. That here RC satisfies it. RC is in the loop, RC is in the circuit. So the collector resistor satisfies it. So again, now design parameters, transistor is BC547, the forward gain is 100. So for LED to sufficiently glow, we need a current of, so that need we limit the current to 5 milliampere using the resistor. So the collector current, maximum collector current is 5 milliampere. VCC is equal to 5 volt and VBB equal to 5 volt. That's we are taking detailed voltage here. And let the cut-in voltage of LED be 2 volt. At the collector emitter loop, this is the equation for RC. RC is equal to VCC minus VC minus VT by IC. That is 5 minus 0.2 minus 2 by 5 milli. That is we are getting collector resistor as 560 ohm. Now according to DC equivalent circuit, the dependent current source is IC here. So when IC equal to 5 milliampere, IB is equal to IC by beta, that is equal to 50 microampere. And at the base emitter, we will write the equation of for RB and rearrange like this. RB is equal to VBB minus VBE by IB. That is VB sat is 0.7. That is we get 5 minus 0.7 by 50 microampere. That's RB is equal to 8.2 kilo. Now another circuit, design of BJT is a relay drive. This is a relay. So in order to drive the relay, there's no need of a resistor here. This inherent resistance acts as a resistance. This coil resistance will be some 200 ohms, and here we will be using a BJT with a higher collector current specification. So we have to design only RB here, and here this is a freewheeling diode. That is, suppose when the relay current changes from high current to zero, that is when the transistor goes from on to off, there will be a big EMF, induced EMF, back EMF here, which will be in polarity with which will be adding to the collector voltage, that is some 50 volt or so. With if we don't use a diode here, this will damage the transistor. So when the transistor goes from on to off, this diode will be bypassing the voltage by current here in order to protect the transistor. So this is called a freewheeling diode. So here we will be using IN4001, which is a rectifier diode. We will be using that. So we have to find RB only here. Suppose this will be an output of a microcontroller, output port of a microcontroller. So it's a freewheeling diode here. So design parameters, now transistor beta is equal to 50. So resistance of the coil of the relay is 200 ohms. So VCC equal to 5 volt, VBB 5 volt. So that is, we are taking TTL voltage here. First step, we have to find the collector current, that is 5 minus 0.2 by 200, that is 24 milliampere. And IB at the base with the DC equivalent circuit, we will be finding IB is equal to IC by beta, that is equal to 480 microampere. So now to find RB, we will write the KVL equation at the base emitter loop. IB is equal to 480 microampere. 5 minus 0.7 by 480 microampere is RB is equal to 8.2 kilo ohm. So we have designed the circuit for relay driver. So other variants are there. So this earlier we have connected LED here. Also we have connected relay here. These two are floating loads. That is only the current. We need only the current. So when we need a voltage here, that is you have to connect a non-floating load. This is suppose, for example, this is a UM66, that is a melody generator IC. This IC needs to be on and off according to the situation for microcontroller. This suppose, for example, we take this as the output of a microcontroller. So we have to control this UM66 IC. So this will be the circuit for that, and here UM66 drives a speaker which makes a sound of a melody tone generated by this IC. So then there is no need of any resistors here. So this will be acting as a switch. So here you can see 5 volt. 5 minus 0.7, we will get 4.3 volt here at the output when the switch is on. So when the switch is here, when the voltage is 0, this here it will be 0, so it will be turning off the IC. So this is another circuit where we have used a PNP transistor. So again this is same just like we have done for LED, but the voltage is inverse here. So when the voltage is low, the LED will be turning on. When the voltage is high here at the port, LED will be off. So the equations for finding out RB and RC is same. You have to first find the on condition. Only the condition is different. At the on condition, this port voltage will be 0. It's a base voltage will be 0, and IC will be maximum at that time. So the transistor will be on when the port voltage is 0. The transistor will be off when the port voltage is high. So need of a current limiting resistance RC satisfies it. So design parameters, transistor is BC557 with beta is equal to 100. So again for LED to sufficiently load, we need a 5 milliampere current, that is IC, and VC and VBB is equal to 5 volt. So let the cut-in voltage of LED be 2 volt. So the transistor goes to saturation when VBB is equal to 0 volt. That is the on condition here. So at the on condition, RC equal to VCC minus VCE minus VT, that is 5 minus 0.2 minus 2 by 5 milli. So that is RC equal to 560 ohm. So again IB we can find IC by beta, that is 515 microampere. So RB equal to 5 minus 0, that is VB, that is when VBB is equal to 0, that is the on condition here. VCC minus 0 minus 0.7 by 550 micro, that will be RB is equal to 8.2 kilo ohm. Next is a H-bridge circuit. This is a circuit to drive a motor forward and reverse. It can be interfaced through a microcontroller or a processor, anything, any FPGA, anything, any such controller to this circuit. Why it is called H means this is in a H shape. See here, this one like this. It is in a H shape. That's why it is called H bridge circuit. And these are the transistors. This is a PNP transistor here. These two PNP transistors. This is NPN transistor. How it works means, to drive the motor forward, this transistor will be on, and this transistor, that is T1 and T4, will be on at an instant, and T3 and T2 and T3 will be off. And so the current will flow like this, see, like this, and the motor will be driven forward. And for reverse action, T2 and T3 will be on and T1 and T4 will be off. So the current flow like this. So the motor will run reverse. This is a DC motor, it has a low resistance, such as for example for 10 ohms like that. And we need a power transistor, a low power transistor to drive this motor. And the switch analogy, see here, this transistor acts, these four transistors act as a switch. This S1, S2, S3, S4, and as I told you earlier, this is a forward movement. S1 and S2, S4 will be on. It's like this action. This two transistors, these are two transistors actually, BJT, that will be on at an instant, and the current will flow like this. And this one, and at this time S2 and S3 will be off, and this is a reverse movement. S2 and S3 will be on. So the logic is like that. So to on this S3 here, there will be a 0 volt here at the base of the transistor 3, and at the base of transistor S2 it will be high. So this here it will be high, this will be low, and here it will be to switch off the transistor. This will be high, and this will be low. S4 will be low. So let us see the all the input combinations for the motor movements. So as I told you earlier, this is a forward movement. So for that, the transistor 1 and transistor 4 will be on, and other two will be off. So because it is a PNP transistor, S1 will be 0. It is a PNP, so it is 0. It will be driven on, and S4 is 1. So that's an NPN transistor, that will be on. So S1 and S4 alone will be on, and S2 and S3 will be off. So this is a NPN transistor, so it is 0, it will be off, and this is a PNP transistor, it will 1, it will be off. And in the reverse, for the reverse movement, S2 and S3 will be on. S2 is a NPN transistor, so that will be high, and this two will be high, this will be on, S2 and S3. So S2 will be high voltage here, logic high here, and S3, that's a PNP transistor, to on that it will be a logic 0, and S1 and S4 will be off. S1 is a PNP transistor, so that will be high, that will be off, and S4 it will be logic 0, so that will be off. It's an NPN transistor, it will be off. So this is a reverse movement. And next is a motor course. Motor course means to bring down the motor slowly to rest. So for that, one combination is all the transistors will be off. For that, it is 1010. You can see you can look at the circuit and find out the values. That is 1010. All the transistors will be off, and this is for this alone. This transistor will be on, so that then at that condition motor comes slowly to rest. And here you can see this alone, this only this transistor is on, that is 1110. And here again S3, this alone this transistor is on, and all these four combinations, the motor comes slow down to rest. And at this condition, here you can see these two transistors S1 and S2 alone is on, that is, this is a PNP and NPN at the left side of the H bridge. This alone will be on. So for that, that happens a short circuit, it's a short circuit, and the VCC will be pulled down to ground. That will cause a short circuit for the battery on the power supply. So these two and here in this combination, S3 and S4 alone will be on. That is again short circuit on the right side. So this combination is not allowed. These two combinations are not allowed. That causes a short circuit. You have to write in the program. If it is an interface to through a microcontroller, you should write the program that says that this combination does not come. And here this is a braking combination. For that the motor come suddenly to stop. That is just like applying a brake for the wheel, like that for a brake of the car as example. It comes suddenly to rest. So that is a braking. This is a braking combination. For that, these two will be on. That is S1 and S3 alone will be on. At that condition, it will comes to a stop. Again, this and 111 means S2 and S4 will be on. So, and that is a combination for braking. So let us see the design for this circuit. So let us see the forward condition alone. T1 and T4 are on, T2 and T3 are off, as I told you earlier. And motor resistance is 10 ohm. Let the transistor beta is 100, and VCC is 5 volt. VB input also is a 5 volt. We are taking TTL voltage for the TTL circuit. For example, for a microcontroller, suppose PIC or 8051 or an Arduino such controllers. You are taking 5 volt here. And first step is find out the collector current. You can see that when two transistors are on, that two transistors will be on and the motor will be on, and we see the motor resistance 10 ohm here, and the cutoff, the VC saturation comes into picture, and those two adding of two transistors, 0.2 and 0.2 added together become 0.4. So the voltage difference or the voltage difference across the motor is 5 minus 0.4 by 10, that is 460 milliampere through the motor. This is the collector current, and since the same collector current is flown through T1 and T4, their base current will be same. So we will take any one of the base current, that is IC by beta. Beta is 100, and this is 460 milliampere by 100, that is 4.6 milliampere. And let us take for transistor 1, that is a PNP transistor. RB1 equal to VCC minus VB1 minus VBB1. So that is 5 minus 0.7 minus 0, that is VB is the saturation for base emitter voltage, and here VBB, we will have for turning the transistor and PNP transistor on, this VBB should be 0. So it is, from this equation we can get 934.78, that is RB1 equal to 910 ohm. Again same for the T4, this time it is a NPN transistor RB2. So that is, and we will give the high voltage at the NPN transistor base. So that is VBB2 minus VB2, that is 5 minus 0.7 by, that is IB current is same current, base current. Since all the transistors are same, we will take the same base current. So that is 4.6 milliampere. 5 minus 0.7 by 4.6 milliampere. You will get 934.7, same thing. And the base resistance is, we can get a standard value resistance, that is as taken before. It is 910 ohm. So since it is symmetrical, for the T2 and T3 condition, for the reverse condition, we will get the same resistance as calculated here, that is 910 ohms again. So this is a required circuit. You can see 910 ohm, and for transistor we are selecting SL100, and this is a diode. As this diode is to prevent the backing off from the motor and to protect the transistor. So these are the diodes here. You take IN414, it is a switching diode. So this is a circuit. So that's it. Please like and share the video, subscribe the channel. I'll be coming with new videos and lectures. Please subscribe the channel. Thank you all. If you have any doubts, you can mail me to chanch484@gmail.com. You can put comments in the comment section. Thank you.